Okay, the time's now 4:30 p.m. Eastern Time. We are going to resume with our next speaker, Faiz Mirza of NASA Jet Propulsion Laboratory, and he will be talking to us about MEXEC, an onboard integrated planning and execution approach for spacecraft commanding. Faiz.
Hi, everyone. So as Chris said, I'm going to be talking about MEXEC today. Next slide. So to give you a quick overview, I'll first give you an introduction, talk about some related work, and then MEXEC specifically, and then talk about some experiments we did on the ASTERIA CubeSat and integrating it and the future work we have planned. Next slide. So why is autonomy important for space missions? Onboard autonomy lets us enable missions where having humans in the loop is infeasible, and this can increase science return, increase robustness, and can reduce our costs. Next slide. Traditionally, spacecraft commanding is done with sequences which specify what to do and when to do it, with commands that have either absolute or relative times. Some sequencers today also allow control logic and event-driven responses. Next slide. But there's not really any information maintained on board about why a command is needed to achieve desired behavior. And because of this, there's a limit to the autonomous behavior. And if something goes wrong, often the response is to go to safe mode. So you can potentially lose science. Next slide. An alternative approach to this is to use goal-based commanding on board. With this, we specify a desired outcome with a goal, and we let the onboard system find an effective use of time and resources to achieve this goal if there is any unexpected events. Next slide. With goal-based commanding, we can maintain intentions and effects on board the spacecraft. These goals can be described through tasks that model spacecraft behavior and constraints. We use an onboard planner with the most up-to-date information to generate conflict-free schedules and effectively use resources, as well as an onboard executive with that same up-to-date spacecraft information to perform real-time constraint checking and to adjust tasks at execution time as necessary. Next slide. Our solution to this is MEXEC, a multi-mission, goal-based onboard integrated planning and execution software. In order to promote infusion of MEXEC and to gain confidence, we develop MEXEC very systematically, methodically prove out its autonomous capabilities, and then we performed flight and testbed experiments on the ASTERIA CubeSat in 2019. Next slide. So ASTERIA was a 6U CubeSat that was developed in collaboration between JPL and MIT. It ran the F Prime Flight Software from JPL, which you've probably heard about earlier in the conference. And it had a 3-axis attitude control box called the Exact Box from Blue Canyon Technologies. We nominally operated ASTERIA with sequences. Next slide. ASTERIA was deployed from the International Space Station in 2017, and it had a successful 90-day prime mission to take precision photometry, take images, and take opportunistic science. And it had 3 extended missions. And during that 3rd extended mission is when we used ASTERIA as a kind of test bed in the sky for technology demonstrations, which included several experiments planned with MEXEC. Unfortunately, we lost contact with ASTERIA a little earlier than anticipated in December 2019. And because of that, the rest of the planned experiments were done on a ground testbed. Next slide. So to give you a quick overview of some related work, VML on Spitzer had higher level programming with sequences and a pre-identified list of observations, but it had no replanning. Remote Agent on DS1 had goal-based commanding, which used model-based programming and onboard search. That flew for 48 hours. ASC on EO1 ran a software called Casper, which maximized science return by creating new goals. And that flew for over 12 years. And then the most closely tied, the M2020 onboard planner, which is scheduled for operational use in late 2021, uses the timeline library that is also used by MEXEC, which I'll talk about soon. Next slide. So MEXEC, as I said, is a multi-mission onboard planner and execution software that works with task networks. It was developed to have a tighter integration between a planner and a controller, which includes a shared model and a shared representation. It was designed to be a component in low-risk heritage flight software, such as F prime. And it allows operators to control the level of autonomy. So whether that be fault protection related items or whether it be total system autonomy. But most importantly, MEXEC was designed to be flown. So it was written to be flight software. Next slide. MEXEC is made up of 3 major components: the timeline library, the planner, and the executive. And it makes 2 major assumptions about the flight software that it's being integrated with. The first is that there is a state database which reports system state. And the second is that there is a command dispatcher to which it can dispatch commands and receive command responses from. Next slide. So MEXEC operates with tasks and timelines. And so first I'll talk about tasks and some task templates. Tasks represent a desired change. So they contain things like an ID, a name, what you want to execute, whether that be nothing, a single command, or if you want to kick off a sequence using some onboard sequencer. They contain impacts, which are the expected effects of either that command or sequence. Constraints, which are the state and resource requirements for executing that command or sequence. Control conditions, which are conditions in the executive, and contingencies, which are actions taken by the planner in case there is some kind of task failure. Templates are very similar to tasks, except they're not explicitly requested to be scheduled. They are added to the planner in order to meet some kind of conflict violation or as a contingency or to meet the precondition of some required task. Next slide. Timelines, on the other hand, are support planning with a representation of past and predicted states and resources. Each state is represented by a timeline, so that's usually real system state for a flight project. These real system states are stored in the state database that I mentioned earlier. MEXEC also supports internal states, which are managed and used only by MEXEC, and these can be used either for simulation cases or for states that don't really match up well with some kind of real system state, usually some kind of transient state. Current state values are updated from the state database. Impacts from scheduled tasks are used to predict the future timeline state, and impacts are also adjusted by feedback from the executive if the executive reports some kind of deviation, whether that be a task running long, short, or just failing altogether. Timelines are created with an initial value and with global limits on the value on that timeline. Next slide. Impacts from the tasks are placed on the timelines and change the timeline value over time by assigning a value, a change in value or a change in rate. This change is then projected forward over time, and aggregation of these impacts create a result at any given time. The constraints are also placed on the timeline, and then conflicts can be calculated for the schedule based on if the constraint is not within the allowed values at a given time, defined by either the global limits of the timeline or by the impacts placed on the timelines. Next slide. So here's a quick example. Let's say that you have a task that requires the camera to be on during the task. You can see at the bottom there, the camera state is off and then on and then off again. So the green interval represents when that task can be validly placed. Next slide. So the planner in MEXEC builds and maintains conflict-free schedules from tasks in the task network. It sends any tasks that are scheduled and ready to go to the executive. It'll consolidate impacts, which is a memory saving step, but also a way to make sure that the state that we have calculated at any given time is correct. It schedules new tasks using a valid interval search from timeline, as I described previously. And then it has 2 optional optimization steps, which are to either try to repair any violations or try to optimize the schedule by shifting tasks closer to their preferred start time. Next slide. And then the executive, which works with the planner, runs on a faster cycle. It'll, as it receives tasks, convert task constraints into a Boolean expression tree, which is then checked during execution. It subscribes to updates from that monitor state task constraints from the state database. Each task follows an internal state machine to monitor its current state of execution, and updates are sent to the planner every time it changes state. Next slide. So now I'll talk a little bit about the experiments that we did on the ASTERIA CubeSat with MEXEC. So for our first experiment, our basic goal was just to integrate MEXEC with the F prime flight software that ASTERIA was using, and prove that MEXEC was mature enough to fly and could be used for the current operations of ASTERIA. Next slide. So our goal was to replicate the behavior of standard ASTERIA sequences by supporting absolutely and relatively timed commands and starting commands no earlier than that absolute or relative times. So we wanted to perform nominal operations to set up passes and take science observations like ASTERIA did nominally. Next slide. So in order to integrate with the ASTERIA F prime flight software, there were several steps that we had to do in addition to just creating components for MEXEC. We created an API to stop and clear MEXEC without having to reset flight software, which didn't exist at the time. We had to really minimize MEXEC's memory usage. MEXEC isn't particularly bloated software, but the memory allocation that we had on ASTERIA, since it wasn't designed for MEXEC, it was a extended mission experiment, was pretty minimal. I think we had 2 megabytes that we could fit into. We wanted a way to reconstruct what MEXEC did in flight on the ground. So we had MEXEC output these binary files that would store information about all the choices that MEXEC made. We also added telemetry, which MEXEC did not have before. And MEXEC didn't support string command arguments when we started, primarily because memory was a concern, but we made it work. Next slide. So the task networks that we designed for experiment 1 were fairly simple. They had no concurrent tasks because sequences that ASTERIA ran had no concurrent tasks, as it only has 1 sequence engine. Each task has 2 pre-constraints, sequence count and the sequence runner mode, and 1 impact, which was to increment the sequence count. Relatively timed commands would start as early as possible while respecting those constraints, and absolute timed commands would start no earlier than their absolute times while also respecting the constraints. And the only constraint is that the sequence count has reached the correct number. So the first task would have a constraint that the sequence count is 0, and have an impact that the sequence count go up by 1. And then the next task would have a sequence count constraint of 1, etc. Next slide. Internally to MEXEC, the development that we had to do, as all the other development was mostly flight software integration work, we created a toggle to disable certain MEXEC features to make some of our testing more simple for the first experiment, i.e. The repair and the optimized steps that I mentioned earlier. And MEXEC is also created with the freedom to define your scheduling algorithms per mission. So we defined a specific scheduling algorithm for ASTERIA. Because ASTERIA was just a pretty simple sequencing case, we had a very simple scheduling algorithm where we just placed all tasks as close to their preferred start time as possible. Next slide. So for our first experiment, we flew for about 16 days. We were able to use MEXEC with ASTERIA to observe HT 219134, New York City, the Moon, and Vesta, and all task networks scheduled and executed as expected with some interesting caveats, which I'll talk about next. Next slide. So the first caveat was that some commands were incorrectly modeled on ASTERIA. All of our tasks in MEXEC would model the sequence counter incrementing at the end of the task when the task is expected to complete. But next slide. Some F prime commands would return that they completed successfully when they successfully dispatched and not when they actually completed. So the sequence counter would increment early while the command was actually still running. Next slide. When this type of task would start late, the next task would be able to start at its scheduled time because it didn't know that the sequence counter was incorrect. And so you'd have this overlap, which is okay with MEXEC and with the command dispatcher, but isn't really representative of the sequence case that we were trying to emulate on ASTERIA. Next slide. There were a few other caveats, but I'll skip over those for now. So our second experiment, which unfortunately we were not able to do on actual ASTERIA and we did on the ASTERIA testbed instead, was to show that MEXEC could react to events and that could have provided some kind of benefit to ASTERIA. So there were more complicated test networks. Next slide. So the scenario that we chose for our second experiment was a momentum management scenario. As I said earlier, the exact has a 3-axis attitude control with 3 reaction wheels and 3 torque rods. External torques would cause momentum buildup, which could cause attitude control loss. And this would cause fault protection safes, and it would reset the spacecraft if a momentum magnitude threshold was passed, which means you could lose upcoming observations, and then you'd have to do reset recovery during a pass. Next slide. In nominal operations, we had ground tools that predicted this momentum buildup and zero crossings. And we would reschedule observations if the ground tools showed unfavorable locations, and we were very conservative with our observation scheduling. With MEXEC, we could be a little less conservative. We would monitor momentum on board and then dump momentum when we reach some sort of limit. This would avoid resetting the spacecraft, and we would be able to resume observations. And we could schedule our observations a little less conservatively so we could improve our data quality. Next slide. So in order to do this, we had to add momentum magnitude to the state database so that it could be transmitted to MEXEC, so MEXEC would be aware. We modeled the constraint and impacts of tasks based on their behavior rather than on sequence count, like we did on the first experiment. And this is really how MEXEC is meant to be used. You model constraints and impacts based on the behavior of tasks. We used a long-running task to monitor momentum. It had a maintenance constraint, which means a constraint over the entire length of the task on the momentum magnitude, and the task would fail when the momentum went too high, which would trigger the executive to start a sequence of commands to dump momentum and return to a known state. It also had a contingency response to add a new momentum monitor and a new observation setup task, and then the cycle would continue once our momentum reached a state that was good again. All science observation tasks were only allowed to occur if the momentum monitor was currently valid, so that they would not schedule, or they would fail, or they would skip if the momentum had currently failed and hadn't recovered yet. But past tasks were allowed to occur at any time unless a fault had occurred, because we always want to communicate with ASTERIA even if the momentum is not doing so great. Next slide. So this is a somewhat simplified example of what the constraints and impacts could look like. This is a visualization tool developed by Ellen Van Wyck, who also works at JPL. We use this in order to debug and visualize what our task networks look like, but this is a somewhat simplified version. Next slide. So this is kind of an example of what it might look like. I'll go through this pretty quickly in the interest of time. Next slide. So at first you can see all the task schedule, and then here the timeline that shows momentum magnitude goes above some persistence level, which causes the momentum dumping response to happen. The 3 tasks with X's on them get skipped, or they stop executing because momentum has reached a point that we don't want it to. Next slide. The next 2 tasks are also lifted because the planner reschedules and removes those tasks because they're in conflict. That second set of tasks are the tasks that were still in the planner and not yet in the executive. Next slide. The momentum magnitude then decreases below the replanning threshold, and MEXEC can start to recover and replan tasks again. Next slide. Since we lost contact with ASTERIA, we ran our experiments on a testbed where we had a real-time dynamics processor to simulate sensor input to the exact. Unfortunately, that RDP did not model all the physics, including some of the torques that the ground tools modeled, which complicated our scenario. So we had to adjust our threshold to reflect the RDP's behavior rather than actual behavior. Next slide. In our experiment, we hit our threshold 4 times and momentum was dumped and observations were resumed each time. Next slide. I'll skip over this. Next slide. This experiment was able to show us that MEXEC successfully responds to onboard state in the planner and executive with task failures, cleanup commands, contingencies, and replanning. We showed that MEXEC could have helped ASTERIA dump momentum and potentially avoid resets if observations were scheduled less conservatively to allow us to increase science quality. Next slide. So now I'll talk a little bit lastly about the state of MEXEC today and what it's been integrated with. MEXEC now has been integrated with F prime, the ASTERIA version of F prime, and also a version of F prime done during a research task earlier. It's also been integrated somewhat with the JPL's Flight Core product line, FCPL. There's a standalone Unix version, which uses Unix messaging library in order to communicate between the different components. It's been integrated with ROS, which is what a Europa lander prototype uses, MEXEC with ROS. And it is now relatively straightforward to integrate with any new flight software. Next slide. In order to integrate with a new flight software, we provide a thread for each, the planner and the controller. We create a state database if one doesn't already exist. We have to define assertions, we have to define EVRs, and create messages between the command dispatcher and the state database, planner, and controller. We have to consider the fault protection ramifications if this is going to fly, and also consider the scheduling algorithm, as MEXEC does allow a lot of flexibility with that. Next slide. So one study that we did near the end and as part of a separate task was how to coordinate MEXEC with the sequencer. As demonstrated with ASTERIA, it's useful to be able to use goal-based commanding and sequential commanding in coordination. Having MEXEC take care of some of the higher level planning and scheduling when task constraints and impacts are well understood helps us a lot, but it would also be useful to use traditional commanding directly for quick and easy sequences of commands, or when the task constraints are not well understood and we want to just issue them in sequence for safety. So on ASTERIA, we were able to issue sequences from MEXEC, and this is the ideal form of interaction that we determined. Next slide. So future work for MEXEC. MEXEC currently is very strict about duration of tasks, so we would want to add some variability to that, be a little more flexible with its execution. We're interested in adding some geometric reasoning support to MEXEC. We also would like to develop some tooling to create and visualize task networks. You saw a little bit of our visualization tooling in my slides, but in terms of creating task networks, it's kind of a hole in our current work. We really would like to have some better tooling. We're also interested in doing some AI explainability work in order to have tools to trace and evaluate MEXEC's planning decisions. And currently the Europa lander prototype team are still adding to MEXEC and are kind of at the bleeding edge of MEXEC's development. Next slide. So in conclusion, MEXEC can be integrated into existing flight software. It can be used for operations, and it has the potential to increase robustness and fail operational commanding. And that's all I have. Thanks.
All right, thanks, Faiz. We have a couple questions in the Q&A from Peter Fiddleman. He says, I'm wondering if you have any more information on how the early versus late incrementing bug was missed and not caught on a test bed, and do you have any recommendations to the audience on how that could have been avoided?
I would say that the way that we caught that was because we realized that the ASTERIA clock timer was not as accurate as we would have predicted. And I think the way that we would have caught that on the test bed would have probably been to do some longer tests. I think some of our testing was a little prescriptive and not general enough. But it also, to some degree for us, was a good thing because we were able to demonstrate a feature of MEXEC that we didn't anticipate. It's something that MEXEC was able to handle, and so because of that, it wasn't something that we concentrated on during our testing, I'd say.
All right, great.
In terms of more general advice on validating goal-based commanding rules, that's something that we're still working on, VNV of task networks in general. There is work being done at JPL currently that I'm not directly a part of, working on VNV of task networks.
All right, excellent. Thanks a lot, Faiz. Great, great presentation. It is now time, and again, as usual, I encourage folks to continue the conversation in Slack.